At this point, we've seen two slightly different situations where Gauss-Jordan elimination comes into play. One of these is where you have a matrix equation, ax equals b, and you want to solve for x. You do this by forming the augmented matrix out of a and b, and then you do Gauss-Jordan elimination, and from that you get the solution. The other situation was finding the inverse of a matrix. And to do that, you can form the augmented matrix where you have A with the identity matrix, do Gauss-Jordan elimination on it, and if A is invertible, then you'll get the identity matrix on the left with the inverse on the right. Now, at this point, you might be starting to feel like you don't really know what's going on when you do Gauss-Jordan elimination. I mean, like, you can do the steps, but do you really understand why it works? In this lecture, we're going to fix that. We're going to learn about what I would say is the right way to think about Gauss-Jordan elimination. And in the process, we'll pick up some tools that will be useful in other ways. It probably is best to start with an example, so let's do that. So let's say we had this matrix and we wanted to do Gauss-Jordan elimination on it. The first step would be to use that 2 as a pivot and eliminate the 4 that's below it. And so to do that, we would subtract 2 times row 1 from row 2, and this is what we get. All right, so now here's something else we could do. Don't ask me why we're doing it yet, just do it. Multiply these two matrices together. Yeah, seriously, press pause and do this multiplication. Okay, this is what you get. It's the same thing that we got when we did the row operation. This isn't a coincidence. In fact, this matrix that we multiplied by, the 1, 0, minus 2, 1 matrix, that has a special property that whenever you multiply it on the left times some other matrix, it has exactly the same effect as doing this row operation of subtracting 2 times row 1 from row 2. And this is not a coincidence. Every row operation has a corresponding what's called an elementary matrix, which is a matrix that you can multiply other matrices by, and doing that multiplication has the same effect as doing the row operation. And there's a simple way to find these matrices. You just do the row operation to the identity matrix. So if you look back at the matrix that we used in this example, that is the matrix that you would get if you did row 2 minus 2 times row 1 to the identity matrix. And there's a simple reason why this is the right thing to do. If we let E be the elementary matrix for a row operation, then on the one hand, E times I should be equal to E, because that's how the identity matrix works. But on the other hand, if E does what it's actually supposed to do, then E times I should be what you get when you do the row operation to I. I'll point out that this argument that I just made doesn't actually prove that it works, but it proves that if it does work, then this is how you find the elementary matrix. To really prove that it does work, you need to think about how matrix multiplication works and see that it really is, when you multiply on the left by a matrix, you really are doing operations that involve the rows. I think if you actually think about what happened in the example that was just done above and how the matrix multiplication works, you'll see that you really are producing combinations of the rows in exactly the right way. So let's just do a few quick examples. Suppose that we're working on a matrix that has 3 rows. And let's think about a few different row operations that you might do. Well, one thing is that you might multiply one of the rows by a non-zero constant. So for example, let's say we wanted to multiply row 1 by 3. Then the corresponding elementary matrix is this one, because this is exactly what you get if you take the 3 by 3 identity matrix and you multiply row 1 by 3. Another row operation you might do is adding or subtracting a multiple of one row to or from another. So for example, you might add 2 times row 1 to row 3. So then this is the corresponding elementary matrix for that, because this is what you get when you do that row operation to the identity matrix. And then finally, you might swap 2 rows. So for example, you might swap row 1 and row 2, and the corresponding elementary matrix would look like this. So an important fact about these elementary matrices is that elementary matrices are invertible. And the conceptual reason for this is fairly simple. It's that all of these row operations that we do, those are reversible row operations. If you multiply a row by a non-zero constant, you can divide back by that constant to get back to where you started. If you add a multiple of one row to another, you can reverse that by subtracting that same multiple. Or if you swap two rows, you can just swap them back. So,
elementary matrices are invertible.
So what is this good for? Well, elementary matrices give us a better way to think about row operations. So let's look at an example. Suppose we want to solve ax equals b, where this is your a and b. How would you go about doing this? Well, the first thing you would do is you would make an augmented matrix, and then you would start doing Gauss-Jordan elimination on it. So the first step would be to use that 1 in the first row as a pivot and try to eliminate the 2 and the 7 that are below it. And so to eliminate that 2, you would do the row operation where you subtract 2 times row 1 from row 2. And then this is what you would get. And then the next step would be to subtract 7 times row 1 from row 3 to eliminate that 7. And then this is what you get. Feel free to just trust my calculations or press pause and do them for yourself just to make sure. Now, in terms of doing the calculations, what we just did is still going to be the best way to do it. But it's useful to think about it in a different way, having to do with elementary matrices. So let's set E1 to be the matrix that's the elementary matrix that corresponds to that row operation that we first did, row 2 minus 2 times row 1. Now my claim is that this matrix that appears in the second step, that's E1 times A. And you could multiply it out just to check that it's true. But this has to be what it is because the way we got this matrix was by doing the row operation. And we already know that multiplying by E1 should have the same effect as doing that row operation. But what about this vector on the right? Well, actually, we know what that is too. It's E1 times B. This one you probably should do the multiplication just to convince yourself that it's right. But again, the way that we got that vector from the original vector was by doing the row operation to the vector. So we do get E1 times B. And then we can do something similar for the second step. We let E2 be the elementary matrix that corresponds to that second row operation. And then we know that the result that we're going to get is E2 times whatever we had before. Now remember that whenever we have one of these augmented matrices, it's really just a way of representing a matrix equation. The first augmented matrix on the far left is the one that represents ax equals b. But now we know that the middle one represents E1 times a times x is equal to E1 times b, and that the one on the right represents E2 times E1 times a times x is equal to E2 times E1 times b. So hopefully you can see what's going on here. We started with a matrix equation, and what we're doing in each of these steps of doing Gauss-Jordan elimination is that we're multiplying both sides of the equation by an elementary matrix. And because the elementary matrices are invertible, this is an acceptable step. It doesn't change the set of solutions. So I like this because it feels more like normal algebra. Like you have an equation and you multiply both sides of the equation by something, and that's an acceptable step. So it turns out that Gauss-Jordan elimination is actually the same thing. It's every step of the process is just multiplying both sides of the equation by an elementary matrix. And the idea is you just keep doing it until the left-hand side of the equation is simple enough that you can read off the solution. So this gives us a better way of understanding what's going on when we do Gauss-Jordan elimination. But there's also something useful that we can get out of this. Suppose you had a matrix A and you knew that you were going to have to solve an equation like ax equals b, but you just didn't have the b yet. Maybe that was data that was still going to come in the future. You could do the steps of Gauss-Jordan elimination because you'll notice that it doesn't matter what the b is. You would do the same steps no matter what. And so you could do those steps with just A to get the reduced echelon form of A, And at the same time, you could keep track of all of the matrices that you're multiplying by to get to the reduced echelon form. So what I mean by that is that even without knowing what b is, we could know that the equation ax equals b is going to turn into the equation rx equals pb, where r is the reduced echelon form of a, and where p is the product of all of the elementary matrices that correspond to the steps of Gauss-Jordan elimination. So you can calculate r and you can calculate p without knowing what b is, and then once you're given the b, you can multiply p times b, and then you've already got your system in a form where you can basically read off the solution without doing very much work. There's an example in the notes that goes through this process in more detail, so take a look at that for sure. And in the next lecture, we'll look at some other things that we can do with elementary matrices.